and then we'll discuss it together. Suppose we have 200 feet of fencing available to enclose 2 adjacent rectangular fields. And these are supposed to be of equal sizes. The question is, what dimensions for the rectangle would yield the largest possible area using the limited fencing material? So you are restricted by this 200 feet of fencing. Like one very extreme situation, something like this. Use your fencing to do something very thin and very long, right? You could do something like this, but usually when you do extreme things like this, you don't end up with the optimal solution. Like this is not going to be the one that gives you the highest possible area. Usually, and you could do something very thin and long that way. Again, that's kind of almost the same, saying the same thing. Usually the optimal solution is somewhere in the middle, the one that will give you the maximum possible area. Okay. Now, so that we can all start working with using the same variables, let me also assign the variables, and then you can take your time to work on this question. Let's say that the width of this outer rectangle is x. So these are x units. And let's say that this the length of the rectangle is y. Again, you could have done this in a number of ways. Like you could have called the smaller side, just this side being y. You know, you could have given different variable names. But if we all start with the same variables, it'll be easier to compare your answer against my answer later. So let's just assume this. So I'm going to give you a little bit of time to work on it, and then we'll come back. So again, earlier we wrote down that the fencing is 200 feet, which corresponds to the perimeter, which is going all around these fields. You have a total of 2y plus 3x. That must be equal to 200 feet of fencing. And we're maximizing the area, so that's the total area of the entire region. That's the length times width of the outer rectangle, which is x times y. Once again, this is our objective function. It has 2 variables. We need to get it down in 1 variable. So I'm going to solve for y in the first equation. So I have 2y equals to 200 minus 3x. And then divided by 2. So y equals 1/2 of 200 minus 3x. Or just everything divided by 2. Of course, you could have also solved for x in this equation. Either one will be just as easy to substitute back in your objective function. So in this case, area equals x times y. But we now know what y is. Y is 1/2. You know what? I'm going to go ahead and distribute this and then put it down there. So 1/2 times 200 is 100. And then minus 3 over 2x. That's what y is. And since area is x times y, now I'm ready to put the y into that equation. And as always, we simplify this function first before we differentiate. Okay, now that we have an objective function in 1 variable in simplified form, what do we do to this? Set the derivative equal to 0. Take the derivative exactly. So take a prime, find a prime. Again, that's really the essence of all of these questions, a simple idea. Setting the derivative equal to 0 is solving these like a large number and type of problems, which is, I think, one of the things what's amazing about this section. It's like the range of problems, like you cannot imagine. When you look at the homework problems, you will see how many different types of questions you can solve with this basic idea. Okay, so derivative of the first one is 100. The next one is minus 3x. Set it equal to 0 and solve for x. You will get 100 is equal to 3x. X is 100 over 3. When you take the derivative of this term, bring the 2 down, right? So you have 3/2 times 2. The 2's cancel. Okay. So at this point, you can convert to a decimal, or if you like, keep it like this at the moment. And then you can, so that way you don't have to do rounding errors. So let's find y now. If you like, before we even find y, let's just check and make sure this is what we were looking for. This is indeed a maximum. So take the second derivative. The second derivative is -3, which is a number less than 0. That tells you it's always going to be concave down. and the point found is indeed a maximum. So now we can go and find y. Y equals, I'm going to go with this equation, y equals 1/2 times 200 minus 3x. X is 100 over 3. The 3's cancel. I have 200 minus 100 inside the parentheses. That's 100 outside waiting to be multiplied in is 1/2, and 1/2 of 100 is 50. And the units, everything was in feet, I believe, so the units will be in feet as well. So we're saying that the dimensions of the rectangle should be 100 over 3 is roughly 33.33 feet by 50 feet. Yes. What was a double prime? If this is your a prime, differentiate it one more time. And the 100 disappears, you were left with -3. So for this question, there was not even an x in the equation for a double prime. So it's always negative. It's always concave down, basically. And sometimes they might also say, you know, what is the largest possible area that you can create two adjacent fields with 200 feet of fencing? In that case, you should also go ahead and multiply the x times y and also report the final answer as an area figure. So again, it wasn't asked here, but if you were to do that, let's just do it for the sake of this example. So 50 times 33.33 roughly is 166.5 roughly square feet. So this is the largest area that you can create with the given amount of fencing and with the criteria that you need two adjacent fields made with that fencing material. Okay, any questions about this one before we try another one? Any questions? Okay. Okay, so on to our new example. Not that one. Let's go back, I think. There we go. So we're going to make a box out of an 8.5 by 14 sheet of paper. So we have our legal size paper. And we're going to make this box by cutting off the corners and then folding the sides up. So what's remaining is basically this is remaining, and so are these sides. Now if you fold the sides up, you will end up with a box. So roughly speaking, not up to scale or anything, but you know, I'm just going to do a box here. Okay. So what I would like to write down, and the question says, what should be the size of the cut X? So if you call this X by X, it's a square piece of paper we're cutting from each corner, then we're folding the sides up. So basically, like you're folding this up and this up, etc. So then you end up with this one. So what should be the size of the cut? So that we end up with the largest box possible. And then they want to know what are the dimensions of the box that you can form for the largest possible box. So first question is, what is it that we're trying to maximize here? The volume. Largest box means maximize the volume. So we want to maximize volume. Volume. Now, volume, we need to write an equation for it. And the only thing we know is really the outside dimensions of this paper. Like this side was, to begin with, this side was 8.5, and this side was 14 inches. Now, when you cut it, X from here, X from here, how much are you left with then for this side of the base of the box? That's, let's say this is the same as this. Would everybody agree? 14 minus 2x, you're cutting x from here, x from there. So that side will be 14 minus 2x. Okay. And what about over here? What are you left with there? 8.5 minus 2x. Okay. And what about the height of this box? When you fold these sides up, what will be the height of the box, which is the same as this? X. The cut becomes the height, right, as I showed you in that figure earlier. So the height of this box will be x. So what can you say then for the volume of this box? Volume in general is length times width times height, right? Volume is length times width times height. So to do that, let's just multiply these three dimensions together. We have x times 8.5 minus 2x times 14 minus 2x. Okay, do we have one or two variables in here? Only one, right? The only unknown is x, right? So in that regard, it's easier. You don't need another equation to get rid of the x. The only thing is this is going to be a little bit messy to multiply. That's the only problem here. But you don't have to basically try to get rid of one variable because you only have one variable, not two variables. So let's go ahead and multiply this out. So volume equals, first I'm going to multiply the x in, which is 8.5, just with this one. 8.5x minus 2x squared. And then we still need to multiply that with the second binomial, which I will do in the next step. Okay, so let's try to do this like a FOIL. So we're going to go, or just go in any order you like. So like 8.5 times 8.5x times 14. Let's see what that is. 8.5 times 14 is 119. So we're getting 119x. Then do 8.5x times negative 2x, negative 17x squared. Then do this times that, negative 2x squared times 14. That's negative 28x squared, right? And then do the last ones, negative 2x squared times negative 2x, which is positive 4x cubed. Can we clean this up a little bit? Can we? The x squared terms we can simplify a little bit, right? So I'm going to also put the highest degree term first. That's 4x cubed. What do you get when you combine negative 17x squared minus 28x squared? Minus 45x squared. And the last one is plus 119x. Now that we have our objective function, we want to maximize the volume, right? We're trying to create the largest possible volume with the same sheet of paper that we have been given. So now the question is, what do you do from this step forward? Okay, so before we do that, okay, so what are we going to do with this? Take the derivative, set it equal to 0, just like our other problems that we have been doing. Okay, take the derivative and set equal to 0. So let's differentiate. We get 12x squared minus 90x plus 119. Okay, I wouldn't even attempt to factor this one out. Numbers are too large, too many possibilities, or it doesn't look like it's going to factor because of that 119 seems such an odd, weird number that may not even have any factors. So what is our alternate route then? If we're not going to factor it, let's use the quadratic formula, which says negative of b plus or minus the square root of b squared minus 4ac, everything divided by 2a, and 2 times 12 is 24. Okay, I'm going to give you a moment. There'll be two answers from here. I'd like to hear both of them. 1.71 for one of the solutions. And what about the other one? I think 5 point something. Good, 5.79 roughly inches. Okay, once again, two answers. Which one do we want? Let's go to the second derivative. As a matter of fact, for this question, you don't even need the second derivative, although we're going to do that. But take a look at the cut of size, roughly 5.8 inches. You know, the width of this paper was 8.5, right? If you cut 5.8 from here, 5.8 from here, there's no paper left even, right? So that solution is not even in the domain of the problem situation. But if you didn't catch that right away, do the second derivative test, and that will tell you that there is going to be a minimum, basically. That's going to give you a negative volume or something like that. But again, in this case, 5.79 is way too much of a cut. You're going to end up with having no papers at all. So that one we can automatically eliminate, or go into the second derivative test, find the second derivative, 24x minus 90, plug in 1.71 first, and then plug in 5.79. And all you have to care is positive or negative. When you plug in 1.71, what did you get? Exactly. So basically, all I'm interested in is that it's a negative number. It's less than 0, meaning it's concave down, and the point obtained there will give us the maximum volume, right? Right. We always plug them into the second derivative. Right. The 1.71 made it negative, right? V double prime evaluated at 1.71. That one was negative. What if, when you evaluate into the 5.79 into the second derivative, what do you get there? You'll get a positive answer, right? That means there is concave up, and that point would be a minimum, so we don't want that one. So we're going to eliminate this one, and we're going to keep the other one. So we're saying that x should be, the size of the cut should be 1.71. Remember earlier I showed you 3 boxes? The best one I showed you, that it was a cut of 1 inch, 2 inches, and 3 inches. The one of 2 inches was the best one, 90 cubic inches. Let's see if this one beats that. Okay, so if you have a cut of 1.71, what will be the volume of this box created? The volume will be, so you have to multiply 3 dimensions, right? One dimension will be 1.71. What about the other dimension? Do 8.5 minus 2 times 1.75. So that dimension seems to be 5.08. And the other side, do 14 minus 2 times x. And that dimension seems to be 10.58. Let's see if we did any better than 90 cubic inches. That was the first estimate I had given you. So multiply these 3 numbers together. Did we do any better? What is the product? So we did a little bit better, 91.9, roughly 92 cubic inches. So the dimensions are these, and the maximum volume you can obtain with that sheet of paper, if you're going to be cutting from one of the corners, the maximum volume you can create is 91.9 inches, cubic inches.